The equations used to calculate voltage drop are applicable to both alternating current and direct current circuits. The voltage drop calculation is the same for both alternating current and direct current. The National Electrical Code, or NEC, does not assume that the input voltage of a system is the same as the output voltage of the system under load. The National Electrical Code allows for a voltage drop of 2% for branch circuits and 3% for feeders. The National Electrical Code does not specify a voltage drop percentage for other types of circuits. However, it is generally recommended that the voltage drop on any circuit should not exceed 5%. In an example where the voltage drop is 7.55 volts, if this is within the 5% limit, then the circuit is acceptable. The formula for voltage drop is voltage drop equals 2 times K times L times I divided by Cm, where voltage drop is the voltage drop in volts. K is the conductor resistance in ohms per 1000 feet. L is the length of the conductor in feet. I is the current in amps. Cm is the circular mils of the conductor. The constant 2 is used for single-phase circuits and the constant 1.73 is used for three-phase circuits. The resistance of a conductor is determined by its material, cross-sectional area, and temperature. The circular mils of a conductor is a measure of its cross-sectional area. The voltage drop on a circuit can be reduced by using a larger conductor size, a shorter conductor length, or a lower current. Let's delve deeper into understanding voltage drop in both alternating current and direct current circuits, expanding on the concepts and providing practical insights for electrical professionals. Voltage drop is an inevitable phenomenon in electrical circuits, representing the reduction in voltage from the source to the load. This reduction is primarily due to the impedance of the conductors carrying the current. Excessive voltage drop can lead to various problems, including reduced equipment performance, overheating of conductors, and even equipment malfunction. Therefore, it is crucial to accurately calculate and mitigate voltage drop to ensure efficient and safe operation of electrical systems. The formula voltage drop equals 2 times K times L times I divided by Cm, as previously stated, is a fundamental equation used to determine voltage drop in both alternating current and direct current circuits. Let's break down each component of this equation to gain a clearer understanding. Firstly, voltage drop represents the amount of voltage lost along the conductor, measured in volts. It is the difference between the source voltage and the voltage at the load. Secondly, K is the conductor resistance, expressed in ohms per 1000 feet. This value represents the resistance offered by a specific conductor material to the flow of current. Different conductor materials, such as copper and aluminum, have different K values. It's crucial to use the appropriate K value for the conductor material being used in the calculation. For copper, a common value for K is 12.9 ohms per 1000 feet, while for aluminum, it is approximately 21.2 ohms per 1000 feet. These values are temperature dependent and typically specified at 75 degrees Celsius. Thirdly, L represents the length of the conductor in feet. It's the one-way distance from the source to the load. For a complete circuit, you need to consider the total length of the conductor, including both the outgoing and return paths. The longer the conductor length, the greater the voltage drop. Fourthly, I represents the current flowing through the conductor, measured in amps. The higher the current, the greater the voltage drop. This is because a higher current requires more electrons to flow through the conductor, leading to increased resistance and voltage loss. And lastly, Cm represents the circular mils of the conductor, which is a measure of its cross-sectional area. Circular mil is a unit of area commonly used for conductors. A larger circular mil value indicates a larger conductor cross-sectional area, which results in lower resistance and reduced voltage drop. Conductor size charts, such as those found in the National Electrical Code, provide the circular mil values for different conductor gauges. Now let's discuss the constants used in the voltage drop formula. The constant 2 is used for single-phase alternating current and direct current circuits. This constant accounts for the fact that current flows through the conductor in both directions, from the source to the load and back. For three-phase alternating current circuits, the constant 1.73, which is the square root of 3, is used instead of 2. This constant accounts for the phase relationship between the three phases in a three-phase system. Now let's consider the National Electrical Code guidelines on voltage drop. As mentioned earlier, the National Electrical Code recommends a maximum voltage drop of 3% for feeders and 2% for branch circuits. Feeders are the conductors that supply power from the service entrance to the branch circuit panel boards. Branch circuits are the conductors that supply power from the branch circuit panel boards to the individual loads such as lighting fixtures and appliances. These voltage drop limits are intended to ensure that electrical equipment receives adequate voltage for proper operation. Exceeding these limits can lead to reduced equipment performance, such as dimming lights or sluggish motor operation. While the National Electrical Code specifies voltage drop limits for feeders and branch circuits, it does not provide specific limits for other types of circuits. However, it is generally recommended that the voltage drop on any circuit should not exceed 5%. This is a good rule of thumb to follow to ensure that all electrical equipment receives adequate voltage. Now, let's discuss some strategies for minimizing voltage drop in electrical circuits. Firstly, using a larger conductor size is an effective way to reduce voltage drop. As mentioned earlier, a larger conductor has a larger cross-sectional area, which results in lower resistance and reduced voltage drop. When selecting a conductor size, it's important to consider both the ampacity of the conductor, which is its current carrying capacity, and the voltage drop. The conductor must be large enough to carry the load current without overheating, and it must also be large enough to keep the voltage drop within acceptable limits. Secondly, shortening the conductor length can also reduce voltage drop. The shorter the conductor length, the lower the resistance and the less voltage drop. This can be achieved by locating the load closer to the source or by using a more direct route for the conductor. Thirdly, reducing the current flowing through the conductor can also reduce voltage drop. This can be achieved by using more energy-efficient equipment or by reducing the load in the circuit. For example, replacing incandescent light bulbs with light-emitting diode bulbs can significantly reduce the current draw and the voltage drop. In addition to these strategies, there are also some other factors to consider when calculating and mitigating voltage drop. These include the conductor temperature, the conductor material, and the type of load being served. The conductor temperature affects the resistance of the conductor. As the temperature increases, the resistance also increases, leading to increased voltage drop. Therefore, it's important to consider the ambient temperature and the operating temperature of the conductor when calculating voltage drop. The conductor material also affects the resistance of the conductor. As mentioned earlier, different conductor materials have different K values. Copper has a lower resistance than aluminum, so using copper conductors can reduce voltage drop. The type of load being served can also affect the voltage drop. Some loads, such as motors, have a high inrush current when they start. This inrush current can cause a significant voltage drop, which can affect the starting performance of the motor. Therefore, it's important to consider the type of load when calculating voltage drop and to use appropriate mitigation techniques, such as using a larger conductor size or a motor starter. To further illustrate the concepts, let's consider a practical example. Suppose we have a 120-volt branch circuit that is 100 feet long and supplies a 15-amp load. The conductor is made of copper and has a size of 12 American wire gauge. Using the voltage drop formula, we can calculate the voltage drop as follows. Voltage drop equals 2 times 12.9 times 100 times 15 divided by 6,530, where 12.9 is the K value for copper, 100 is the conductor length in feet, 15 is the current in amps, and 6,530 is the circular mile value for 12 American wire gauge conductor. A calculated voltage drop is approximately 5.9 volts. The percentage voltage drop is equal to 5.9 volts divided by 120 volts times 100%, which is approximately 4.9%. Since the percentage voltage drop exceeds the National Electrical Code recommended limit of 2% for branch circuits, we need to take steps to reduce the voltage drop. We could use a larger conductor size, such as 10 American wire gauge, which has a circular mil value of 10,380. Using this larger conductor size, the calculated voltage drop is approximately 3.7 volts, and the percentage voltage drop is approximately 3.1%. This is still slightly above the National Electrical Code limit, so we could further reduce the voltage drop by shortening the conductor length or by reducing the load on the circuit. In conclusion, voltage drop is an important consideration in electrical circuit design and installation. By accurately calculating voltage drop and implementing appropriate mitigation techniques, we can ensure the efficient and safe operation of electrical systems. The formula voltage drop equals 2 times K times L times I divided by Cm is a fundamental equation used to determine voltage drop in both alternating current and direct current circuits. The National Electrical Code provides guidelines on voltage drop limits for feeders and branch circuits. Using a larger conductor size, shortening the conductor length, and reducing the current flowing through the conductor are effective ways to minimize voltage drop. By considering these factors, electrical professionals can design and install electrical systems that meet the National Electrical Code requirements and provide reliable power to electrical equipment. Now let's elaborate on the importance of conductor selection in minimizing voltage drop. The choice of conductor material and size plays a crucial role in determining the overall voltage drop in an electrical circuit. Copper and aluminum are the two most commonly used conductor materials, each with its own advantages and disadvantages. Copper has a lower resistivity than aluminum, meaning it offers less resistance to the flow of current for a given conductor size. This translates to lower voltage drop compared to aluminum conductors of the same size. However, copper is also more expensive and heavier than aluminum. Aluminum, on the other hand, is lighter and more cost-effective than copper, making it an attractive option for long cable runs or applications where weight is a concern. However, due to its higher resistivity, aluminum conductors require a larger cross-sectional area than copper conductors to achieve the same level of voltage drop performance. Therefore, when selecting a conductor material, it's important to consider the trade-offs between cost, weight, and voltage drop performance. In addition to conductor material, the conductor size also has a significant impact on voltage drop. As mentioned earlier, a larger conductor size has a larger cross-sectional area, which results in low resistance and reduced voltage drop. Conductor sizes are typically expressed in terms of American wire gauge, where a smaller gauge number indicates a larger conductor size. For example, a 10 American wire gauge conductor is larger than a 12 American wire gauge conductor. When selecting a conductor size, it's important to consider both the ampacity of the conductor and the voltage drop. The ampacity is the maximum current that a conductor can safely carry without overheating. The National Electrical Code provides ampacity tables that specify the allowable ampacities for different conductor sizes and insulation types. The conductor must be large enough to carry the load current without exceeding its ampacity rating. In addition to ampacity, the conductor must also be large enough to keep the voltage drop within acceptable limits. As we've discussed, excessive voltage drop can lead to various problems, including reduced equipment performance and overheating of conductors. Therefore, it's crucial to select a conductor size that meets both the ampacity requirements and the voltage drop requirements. In some cases, it may be necessary to use a larger conductor size than required for ampacity in order to meet the voltage drop requirements. This is particularly common in long cable runs or in circuits with heavy loads. To determine the appropriate conductor size for a given application, it's necessary to perform voltage drop calculations using the formula voltage drop equals 2 times K times L times I divided by Cm. This calculation will provide an estimate of the voltage drop that can be expected for a particular conductor size and load conditions. If the calculated voltage drop exceeds the National Electrical Code recommended limits, then a larger conductor size should be selected. It's also important to consider the dating factors that can affect the ampacity of a conductor. Dating factors are adjustments that must be made to the ampacity of a conductor when it is installed in certain conditions, such as in a hot environment or in a conduit with other conductors. These dating factors reduce the allowable ampacity of the conductor, which may necessitate the use of a larger conductor size. In addition to conductor selection, there are also other techniques that can be used to minimize voltage drop in electrical circuits. One such technique is to use multiple conductors in parallel. This involves connecting two or more conductors of the same size in parallel to carry the load current. This effectively increases the cross-sectional area of the conductor, which reduces the resistance and the voltage drop. The use of parallel conductors is permitted by the National Electrical Code, subject to certain conditions. Another technique that can be used to minimize voltage drop is to use voltage-boosting transformers. These transformers are used to increase the voltage at the load end of the circuit, which can compensate for the voltage drop that has occurred along the conductor. Voltage-boosting transformers are typically used in long cable runs or in circuits with heavy loads. In summary, conductor selection is a critical aspect of electrical circuit design and installation. The choice of conductor material and size has a significant impact on the voltage drop in the circuit. By carefully considering the ampacity requirements, the voltage drop requirements, and the directing factors, electrical professionals can select the appropriate conductor size for a given application. In addition to conductor selection, there are also other techniques that can be used to minimize voltage drop, such as using parallel conductors or voltage-boosting transformers. By implementing these techniques, electrical professionals can ensure that electrical equipment receives adequate voltage for proper operation and that electrical systems are safe and reliable.